uh, transistor equivalency. When two transistors are equivalent if the ratio of either W by L is equal independent of the absolute values of W or L. This theorem is depicted pictorially in figure. His statement is obviously since the large signal IV equations are only functions of W by L. In reality, there are second order effects that make this statement only approximate. A transistor with a smaller W tends to have slightly less current than that predicted by equation due to the cross section of the channel as viewed along the channel being rounded rather than square. Also, a transistor with a shorter length tends to inaccuracies due to short channel effects because of the second order effects. Transistors having wide large W's 52,000 nm usually realized by connecting a number of smaller transistors with W's on the order of 10 to 25 nm in parallel. As we will be doing only approximate analysis by hand, these second order effects will be ignored. You can see in this figure scaling both W and L of a transistor has no effect on a first order approximation. And in this figure, two transistors in parallel Q1 and Q2 having equal L's are equivalent to a single transistor having width equal to the sum of the widths of Q1 and Q2. Two transistors with the same length connected in parallel are equivalent to a single transistor having a width equal to the sum of the widths of the two transistors. This theorem is depicted graphically in figure. The proof is simple and straightforward. Assume there are two transistors Q1 and Q2 having identical lengths L and widths W and W2 respectively. Furthermore, assume for their gates, sources and drains are all connected together and the transistors are all in the active region then the total current IT is given by IT equal to ID minus 1 plus ID minus 2 equal to nu C naught X by 2 into W1 plus W2 by L into VGS minus VT square. But this is the IV equation of a single transistor having a width W1 plus W2. A similar proof can be given for transistors in the triode region. If the lengths of the transistors are not equal, then one of the transistors can have both its W and L scale according to the theorem 1. To make the lengths equal, and theorem 2 can then be applied to simplify the network. And theorem 2 can then be applied to simplify the network. 3. Two transistors having equal widths connected in series and having their gates connected together are equivalent to a single transistor with a length equal to the sum of the individual lengths. This theorem is shown pictorially in figure. The proof of this theorem, although straightforward, does require a little algebra. Q1 will certainly be operating in the triode region since its drain source voltage is small and has current given by ID minus 1 equal to nu C naught X W by L1 into VGS minus 1 minus VT v ds minus 1 minus v e square ds minus 1 by 2. Here you can see in this figure two transistors Q1 and Q2 having equal W's and connected in series with their gates connected together are equivalent to a single transistor having a length equal to the sum of the lengths of Q1 and Q2. Assuming Q2 is in the active region and its gate source voltage is given by VGS minus 2, VGS minus 2, VGS minus 2 equal to VGS minus 1 minus VDS minus 1. Then the drain current of Q2 is given by ID minus 2 equal to nu C naught X by 2 W by L2 into VGS minus 1 minus VDS minus 1 minus VT whole square is equal to nu C naught X by 2 W by L2 VGS minus 1 minus VT minus VDS minus 1 whole square expanding equation we have RD minus 2 equal to nu C naught X by 2 W by L2 VGS minus 1 minus VT square whole square minus 2 VGS minus 1 minus VT VDS minus 1 plus VDS square minus 1. Since ID minus 1 is equal to ID minus 2, we equate equations and rearrange to get W by L1 plus W by L2 VGS minus 1 minus VT VDS minus 1 minus W by L1 plus W by L2 V square ds minus 1 by 2 is equal to 1 by 2 W by L2 VGS minus 1 minus VT whole square. That implies that equates VGS minus 1 minus VT VDS minus 1 minus V square ds minus 1 by 2 equal to 1 by 2 L1 by L1 plus L2 V GS minus 1 minus VT whole square. Substituting equation into equation, we will get ID1 equal to nu C naught X by 2 into W by L1 plus L2 into VGS minus 1 minus VT square 80 whole square. That this is the IV equation of a single transistor having length L1 plus L2, and the proof of this completed if Q2 had been in the triode region, a similar proof is possible. That this is left as an exercise for the reader. As before, if widths of Q1 and Q2 are not equal, then one of the transistors will be scaled and the circuit can be simplified. It is now possible to describe a procedure for simplifying the network of drive transistors of an NMOS gate to either an open circuit or a single equivalent transistor. All transistors that have zero inputs at their gates are off and can be eliminated from the circuit. To any transistors in series with any transistors in series with the transistors that are off can be eliminated from the circuit. 3. All the remaining transistors have equal gate voltages. Therefore, theorems 1 and 3 can now be repeatedly applied to replace parallel and series connections by equivalent transistors until until eventually a single transistor or an open circuit results. This procedure is best illustrated by an example. Thank you.